So let's use the thin lens equation. So we labored to derive this, and we have a whole bunch of sign conventions. So I'm going to say plus sign convention that you guys got to remember. So let's do an example. So let's say that I have a 5 centimeter object that's 30 centimeters from a diverging lens with a focal length. Note those sneaky absolute value bars of 15 centimeters. Find and characterize the image. So what I would do with all physics problems actually is draw a picture. And let's put the object on this side just to be a little bit different. So I have an object height of 5 centimeters. That's what 5 centimeter object means. Really 5 centimeters off of some arbitrary location, the principal axis. And then we have a diverging lens. Yuck. We have a diverging lens which has the diverging lens icon. Beautiful picture. And I have this thing 30 centimeters away, so that means that D naught is 30 centimeters. And I have a focal length of 15 centimeters. So the first question is, where should I put this focus? So this and this basically are free. It's wherever we choose to place them. But the focal length, so for a diverging lens, I got to put the focus where the focus should be. So the focus should be on, in this case, this side, and half the distance, so about there. So F. And technically that's F when we use our sign convention. Two ways of thinking about it. One way of thinking about it is focal length is negative for diverging lenses. The second way of thinking about it is anything that didn't make it through the mirror is negative. So D naught is positive, and any image or focus on this side would be negative. Okay, but one way or another, this is what we have. So what I would do is always, just to make sure, sanity check on the answer, is I would really quickly sketch a ray diagram. So I've got ray 1, which is in parallel out as if it came from the focus. So for ray 2, I'm going to need our focus on the other side. So focal length here, F. And I'm going to try to make it there, but I'm going to diverge away. So try to make it there, diverge away, and then this is the in focus out parallel ray, and then finally I got a third ray, which just goes right through the center and nothing happens. So clearly these themselves don't converge, and what we're going to end up with is a virtual image. And if I trace these back, so that was pretty quick and dirty, but looks like we'll get an upright, as always, virtual image, and maybe it's located at like, I don't know, 5 to 10 centimeters or something. I don't know how seriously to take this. But again, the way you think about this is sanity check. So the actual numbers, just got to go into the sign convention. So I have 1 over F is 1 over DO, 1 over DI. I know that that's negative because it's a diverging lens. I know that this is positive because it's always positive. I'm using the same units. They don't have to be SI, but I do have to use the same units. 1 over DI, and then math happens. That's 2/30ths, that's 1/30th. I subtract them, I get negative 3/30ths, or DI is negative 30 over 3 or minus 10 cm. Okay. So negative is what we want. This is on the negative side. It didn't make it through the lens, so the negative checks out with the ray diagram. So I'm happy about that. And then the last thing we have is the same exact kind of auxiliary equation we got for the lateral magnification will also work here. HI over H naught, and when we drop those minus, or the absolute value bars and got minus signs, I still have this. So this still works. This is the second equation that came out of those two similar triangle diagrams that we drew to derive that, quote unquote. So HI is what we're looking for. H naught is 5 centimeters, again, positive because it's always positive. And then this is minus DI, so it's minus 10 cm over 30 centimeters. So this is defined as the lateral magnification. So one way of just saying it is just consider this quantity. is this is magnification of 1/3. So, if we drew this picture precisely, this would be 1/3 the height of that. So that's really what magnification means, nothing, surreptitious about it. So I have m equals 1/3, positive 1/3. The positive means they're both upright, object and image. And I would say that hi is 1/3 of h naught, so that's 5/3 of a centimeter. We hate fractions in physics, but idea for that, so we'll call it 1.67 centimeters. But positive is important because it's upright. So the fact that both hi and di carry signs that are meaningful, positive means it's upright. So that would be one of the harder ones because diverging lenses have sneaky signs in them. They have a negative focus, and in this case we had a virtual image on the same side, so that would be a negative image distance as well. Okay, so the last topic to cover, and we'll do a couple more examples of these, is where do foci come from in the first place? So this is what's called the Lensmaker's equation. And I know we wrote it down once and kind of argued a little about what it needs to be. And the reason to include it, even though it's a little bit out of the sequential flow of the textbook, is that honestly most of the lenses that you come across in real life, especially like corrective lenses for vision, are meniscus lenses. And meniscus lenses are hard to deal with just by looking at their, asking about their focal length. So the Lensmaker's equation gives us our answer for whether or not a meniscus lens with a convex and a concave side is diverging or converging. So I've got a lens, and it's got 2 radii. So we'll just draw, converging one, just really vanilla lens to get things started. And what I have is, we'll call it R1. So the first radius of that curvature, and then we have R2, which the way I've drawn it is much tighter. So this might be here, like R2. It would be true if, for instance, I had a diverging lens where I would have R1 and R2. Call it R2 because it doesn't matter, and R1, or it would be true if I had a meniscus lens with one or the other of them. So R1 and R2. So any lens that you draw, any thin spherical lens, will have 2 radii, and each one will have a type, either concave or convex. So in the case of a meniscus lens, both of the centers are located at on the same side. So this is shady picture of a meniscus lens. We'll call that R2 and that R1. As it turns out, it doesn't matter which one's R1 and which one's R2. So this is a moment where you guys get to pretend that you're theoretical physicists. And the way that theoretical physicists work is they just kind of stare at the thing and say, what could this possibly depend on? And then if they're lucky, they write down the answer just based on that. So I've got a lens, and what could the focal length of the lens possibly depend on? So which is to say, f the focal length of the lens, what could it be a function of? Clearly the geometry. So it's got to be a function of R1 and R2. What else could it possibly depend on? Can't hear you. Okay, so probably most people said the material itself. So the index of refraction of the material. You're right. If you're really kind of sharp thinking about this, and you remember Snell's law, there are actually 2 indices of refraction in Snell's law. What you care about is what you're leaving and what you're entering. And then on the back side of the lens, what you're leaving and what you're entering. So honestly, technically, if you have a lens that has some focal length and it's printed on the side, they're assuming it's in air. And if you took it and you dunked it in water, it would actually have a different focal length. So honestly, the full description of this would depend on both the index that you're leaving and the index of the lens itself. So I'll call this an M for medium and an L for lens itself. So in words, this depends on both radii. And just like with mirrors, radii of curvature will carry signs. And it also depends on both index of refraction. Turns out this is not an easy thing to prove. I don't even know if it's in the text. I don't think it's worth subjecting you guys to it. But the full, actually I know the full derivation with both indices is in here. So I'll write that just so you guys know. And I've seen this once. I'll just tell you outright, I'm not going to ask you questions about this, but this is really the full Lensmaker's equation. Again, if I had, and you know this if you've ever opened your eyes underwater, is that all of a sudden, it's like pretty hard to focus. And what you've done is you've changed the medium in which your eyes are trying to focus from air, which is essentially n equals 1, to water, which has an index of refraction of 1.33. So this is actually for any media. So your lens is in space, your lens is in air, your lens is in water, your lens is in molasses, whatever. Specifically for air, and this is the one that we'll see a lot, is n lens minus 1. So the medium air is 1, 1 is close enough. 1 over reciprocal indices added together. So this is the usual form that we'll see the Lensmaker's equation. This also carries signs. So it must. You're never going to get a lens material that's less than 1. If you actually have an index of refraction that's less than 1, you're traveling faster than the speed of light, which is good for you, but don't do that in my class. So really the sign diverging or converging comes from these. So we actually have a sign convention there too. Yes, yet another sign convention. And that sign convention is that if we have a concave side, it's negative. So this is a concave side. And positive is a convex side. So a couple of properties of this, which will make a lot of sense based on some of the discussion we had. First and foremost is that I have two things added. If I flip R1 and R2, so you may have been wondering, how do I know which one's R1 and which one's R2? Turns out it doesn't matter, because this plus this doesn't matter if I flip them. This is good. What this means is that lens has a single focal length. So because 1 over R1 plus 1 over R2 equals 1 over R2 plus 1 over R1, it doesn't matter which side the light is coming in from, it has the same focal length. So for instance, if I have a really, I'll just ridiculously exaggerate this, really shallow radius of curvature and really steep radius of curvature, this focal length and this focal length will be the exact same, right? So lenses have only one numerical value of f. It just appears on the same side, right? Strongly curved on this side, weakly curved on that side is the same as weakly curved on that side, then strongly curved on that side. So focal, doesn't matter which way it works. So you can verify this experimentally if you're a glasses wearer by turning your glasses upside down, and things seem a little bit weird, but they still work. So it doesn't matter which way you flip the lens. And the second property of this, which is useful, is this lets us, again, find the focal lengths of meniscus lenses. So if we have two concave sides, they're both negative. Clearly this is negative, negative and negative. If we have two convex sides, positive and positive, clearly this is positive. If we have a meniscus lens, it's unclear because one's positive, one's negative, until we put them into the Lensmaker's equation. So it predicts the behavior of meniscus lenses, i.e. whether or not they converge or diverge. And to do that, we'll just do a quick example with a meniscus lens. So meniscus lenses are kind of funky. We'll figure out something that's actually like pretty close to a corrective lens. And the first thing to do is to sketch the thing. So I'll just do this all in words. And this is my really feeble attempt at a trick, is I just give an R and put it in absolute value signs and tell you it's concave. What you guys need to do is just remember the sign convention that concave sides are negative. So if it holds water, it's something that's going to be a diverging lens element, so that's negative. Honestly, everything kind of traces back to just knowing diverging lenses have a negative focus, therefore they must be made out of negative sides. So the last thing I need to do is tell you, and we'll do it once, just explicitly stating that the lens is operating in air. So this lens is operating in air, and it's made out of some, optical glass with index of refraction 1.5. And honestly, I don't know, maybe on a mini project, but not, nowhere else, I'll ask you about the full Lensmaker's equation of just, you should realize at least qualitatively that when you go underwater, this is why your eyes have trouble focusing, is that the Snell's law, it doesn't bend as much as it used to, because it's also in a heavier medium. Okay, so let's draw this first. I have a meniscus lens, and I could draw two types of meniscus lenses. I could draw one that looks like this. So the convex big radius and the concave shallow radius, or I could draw one that looks like this. And for most of us glasses wearers, we own a couple of those. So this one has a convex side with a radius of 80 centimeters and a concave side of a smaller radius. So which one of these is that? Yeah, big radius there and small radius here. So this is a big convex radius. So we'll call that R convex. Water would fall off of it. And then the smaller one is concave. So this is the smaller radius. And unfortunately, I really like this purple marker, but it's dying. So this would look something like this particular meniscus lens. And then we have a Lensmaker's equation, and we just got to make sure we have the signs right and dump stuff in. This is the Lensmaker's equation acting in air, 1 over R1 plus 1 over R2. Doesn't matter which one's R1 and which one's R2, it just matters that we get the signs right, because if you flip them, it doesn't matter. So 1.5 is the material we're made out of, -1, and then, again, doesn't have to be SI, it just has to match. So the 80 is positive, that's the convex, so 80 centimeters. And then this is -40, so the concave would be a negative sign. Okay, and then honestly, like a little bit more math than I can do in my head happens. 0.5 minus, what was that, -2 ABS, so -1 ABS. Actually, that's not true at all. So that's minus 160 centimeters. So focal length of minus 1.6 meters. So that's pretty significant, right? So the important part is what type of lens is this? So just looking at, you can figure it out once you kind of have the key. Shouldn't have scribbled that out. Is this a converging or a diverging lens? I see negative on the focus, so this is a diverging lens. And I can kind of imagine that this thing got a little bit melted, and if I redrew it, it might actually look like a diverging lens, at least the icon. Likewise, if I kind of melted this and smushed it out, this might look like a converging lens. So basically what happens is the shallower radius of curvature wins. So this really shallow radius of curvature, it's really, really deep. This side's going to win. This is the negative side. And this really deep side, the shallow radius of curvature, is going to win. This is going to be conversion. Okay. So with that, you guys basically know classical geometric optics. What we haven't covered is cool things to do with this. So we're going to go to optometry school for about 40 minutes and build some telescopes, and then talk about where this stuff kind of fails. So dispersion, rainbows, spherical aberration, etc.